Welcome to today's webcast series presentation, Roundabout Fastest Path, Fastest Speeds, and Speed Consistency Calculations as per NCHRP 672 and TORUS. My name is Bob Drake, editor of Civil and Structural Engineer magazine, published by Zweig Group. Thank you for joining this webcast, which is sponsored by Transsoft Solutions. Before we begin today's presentation, first some general information about the webcast and the webcast platform. The views of the speakers and organizations participating in this webcast are their own and do not necessarily reflect those of Civil and Structural Engineer or its publisher, Zweig Group. If you have any technical difficulties while viewing this webcast, please submit questions or a brief explanation of your technical problem using the Ask a Question box on the left side of the webcast dashboard, and a representative will assist you. Note the button in the upper right corner to enlarge the slide viewing window if desired. During the webcast, you also can submit questions to our speakers using the same Ask a Question box. Submit your question at any time, and we will try to answer as many as we can later in the webcast. Zweig Group encourages group learning for our events. If you are viewing the live webcast with a group on one registered person's computer, that person must complete and submit the multiple viewer registration form for the group in order for everyone to earn credit. Download the multiple viewer registration form from the event resources on the left side of the webcast dashboard. Submission instructions are on the form. Also note a link in the event resources section to download a PDF of the slides in today's webcast. Details on downloading a certificate of completion will be provided later in the webcast. And viewers of archived webcasts must pass a quiz in order to download a certificate of completion. Additionally, at the end of today's event, we will provide a webcast evaluation survey for you to submit your feedback. Today's presenters are Johan Flores, Product Manager with Transsoft Solutions, and Hannah Khosravi, Civil Designer with Transsoft. So let's get started. Johan, I'll hand it over to you.
Thanks, Bob. Hi, everyone. My name is Johan Flores. I'm one of the product managers here at Transsoft Solutions. With that said, just maybe a short company introduction before we proceed on with the main body of our presentation today. So in terms of Transsoft Solutions, last year actually marked our 25th anniversary. We've been at it developing software for AZ Professional, specifically for the transportation people. With that said, our products are used in over 100 countries and by thousands of engineers and architects worldwide. And basically, our claim to staying power really is just being able to listen to the suggestions that are being provided by our users and tailor making our products to provide them solutions to their everyday needs. So without further ado, let me introduce my colleague here, Hannah, and she'll walk us through the theory portion of this. And then later on, we'll look at some of the practical things in our presentation.
Hello, everyone, and welcome to this session. Well, this is our today agenda. Firstly, I will describe what is the fastest path, and then I'm going to show the different types of the fastest path, plus the 5 critical radii, which are important for designers and engineers to consider for roundabout designs. For the next step, I'm going to talk about how we can generate the fastest path and use this method to estimate roundabout speed. After that, I'm talking about the speed consistency and its importance for roundabout safety. At last, I will show you the workflow that engineers and designers using to create the fastest path and speeds manually step by step. Then my colleague is going to demonstrate the TORUS Roundabout design software in terms of creating the fastest path and calculating speeds. Well-designed modern roundabouts usually bring advantages over intersections. For instance, improved capacity and safety for drivers, pedestrians, and cyclists. The geometry at entry, circulatory, and exit of roundabouts is important to assess the speeds at the roundabout. And the fastest path analysis estimates the speeds along the vehicle path. The fastest path is the smoothest, flattest path possible for a single vehicle in the absence of other traffic and ignoring all lane markings. It's drawn for a vehicle passing through the entry, circulatory, and exit for all movements. The fastest path allowed by the geometry determines the negotiation speed for that particular movement into, through, and exiting the roundabout. The design speed of the roundabout is also determined from the smallest radius along the fastest path, and usually the smallest radius occurs on the circulatory roadway when a vehicle turns to the left around the central island. This slide illustrates the three types of fastest paths, includes through, right turn, left turn movements. Also, the 5 critical radii that must be checked for each approach. The R1 through R5 are minimum radii, which represent the vehicle center line in its fastest path through the roundabout. Regarding to NCHRP 672, to generate the fastest path, a vehicle is assumed to be 2 meters or 6 feet wide and maintain a minimum clearance of 50 centimeters or 2 feet from a roadway center line or concrete curb and flush with a painted edge line. In this slide, the vehicle path, center line, and offsets are shown for the single lane and multi-lane roundabouts. The fastest paths must be drawn for all approaches and all movements, including left turn movements, which generally represent the slowest of the fastest paths, and also right turn movements, which may be faster than the through movements at some roundabouts. For the through movements, the fastest path is a series of curves. To draw the path, a short tangent should be drawn between curves, which gives time to driver to turn the steering wheel. To measure the minimum radii, engineers use the curve template or replicate the path in CAD and try to define the radii based on their engineering judgment. The entry path radius, R1, is a measure of deflection imposed on a vehicle before entering the roundabout. The construction of the fastest path should begin at least 165 feet or 50 meters before the entrance line or yield line by using the appropriate offset which identified above. For example, R1 should be measured at the smallest best fit circular curve, and the length of the arc should be at least 20 to 25 meters or 65 to 80 feet near the entrance line. After determining the radii, the relationship between travel speed and horizontal curvature is calculated with the following equations, which are useful for different superelevation values, positive and -2%. As you can see, this method doesn't consider the effects of deceleration and acceleration. So for the cases where the path radii are large, it may overpredict speeds happening at the entry and exit. So to achieve the better results for V1 and V3 calculation, I mean the entry and exit speed, two equations recommended based on NCHRP 672. These speeds are critical to estimate for designers and engineers when they design the roundabouts. This slide shows the V1 and related parameters. And then the next slide shows V3 and its parameters, which gives more accurate values for entry and exit speeds. In addition to achieving an appropriate design speed for the fastest movement, achieving consistent speed for all movements is another important objective for roundabout design. Speed consistency between the speeds of various movements can help to minimize the crash rates between conflicting traffic, so optimizing entry capacity. Relative speeds between conflicting traffic streams and between consecutive geometric elements should be minimized. Based on NCHRP 672, the maximum speed differential between movements should be no more than approximately 10 to 15 mph or 15 to 25 km per hour. Also, based on FHWA, the value for R1 must be less than R2, and also the value for R2 must be less than R3. This condition ensures that speeds will be reduced to the lowest level at the roundabout entry and will reduce the likelihood of loss of control crashes. Now, I would like to show you how we can create the fastest path and measure radii using CAD to calculate speed manually. Generally, manual method has 4 main steps based on a Wisconsin Department of Transportation Roundabout Guide. First of all, we should create offsets for our roundabouts. 1 meter offsets from medians and 1.5 meters from the central island and corners, as you can see in this image. Also, regarding to NCHRP 672, the fastest path must start at least 15 meters from ICD. In the next step, we should draw a spline curve as shown in this slide for the through movement. To get the better result, we should select points A through C on the offset from Splitter Island. It is advisable to choose first 2 points, I mean A and B, outside the 50 meter by about 8 meter interval, and the last one, C, exactly on the 50 meter arc from the ICD. Next, we should choose point D close to the 1.5 meter offset from entry curve. Then choose a location for S-line near to 1.5 meter offset from the central island. After that, we need to select the position for point F close to the 1.5 meter offset from exit curve. For the last part, we should use the same approach which we used at the beginning of the vehicle path. Choose point G on the exactly 15-meter distance from ICD and other 2 points after 50 meters by about 25 feet or 8-meter interval. Select another point which defines J in this image just upstream from the first point of the S-line. To select the tangent direction from the drop-down menu as it is shown in this slide. This will force the S-line to be tangent to the splitter island offset, and do the same thing for the end point by selecting another point named K in this picture. In the next step, we need to modify the spline, which created in step 2, to see if it violates the offset. By zooming, we can visually inspect whether the spline curve violates the curve offset. If yes, we will need to modify it. Once an acceptable spline is created, it is the time to measure our values by fitting arcs to the spline. Using nearest object snaps to fit an arc onto the spline at a point that appears to be the tight portion of the spline. This should happen before to the yield line and not more than 50 meters from the yield line. Then we should check the length of the arc, and if the arc is not 20 to 25 meters long, we should recreate it. Then we can measure the radius of arc. We must repeat this process to find R values for all movements. And after finding the values for R, we need to calculate speed for each R. Now I would like to show you these steps in CAD. So let me switch to the CAD. Now at the moment, I would like to share my screen with you to show how we can create the fastest path in AutoCAD platform. It takes some seconds to show you. Thanks for being patient. I hope you can see my screen. If you have any trouble, let me know. Now, this is the CAD platform, and I would like to show you how we can create the fastest path and can estimate the speed for this roundabout. This is a single lane roundabout with 4 legs, which I designed before by AutoCAD. And now I need to generate through movement fastest path and estimate speed for entry, circulatory, and exit. First of all, I need to create the offset. 1 meter offset for splitter island, for entry and exit. And also 1.5 meters offset from the central island and also enter and exit corners regarding to NCHRP 672 methodologies. And also these 2 red arcs that we have here represent the 15-meter distance from ICD, which is important for us to create the fastest path and measure the radii, especially R1 and R3, I mean the entry radius and exit radius. And after that, I need to find the best fit spline to join all the offsets together to create the vehicle path. Also, I need to go and turn on the snap and then select the 1 point outside the 50-meter arc and the second point by 8-meter interval and the third point exactly on the 50-meter. And then I need to continue along the offset. I try to select the segment very small, but as you know, this is a drawing example, and because of time issue, I just to show you the methodology, but in a real drawing, we need to spend much time to get the best result. In this case, I activate the near object snap to find a better spline. I try to show you the methodology of these dots that they recommended for fastest path creation and speed calculation. Again, for the end, I need to select 1 point exactly at a 50-meter distance from ICD and 2 points outside the 50-meter to become sure this is tangent to the splitter eyelet. Now I create this spline. And I need, in the next step, I need to go back and check the spline. And if the spline violates the offsets, I need to edit and modify it. I start from the beginning. For example, here somehow we need to move the points. And again here, I need to move the points. And here we have a kink, so I'm going to modify it to get the better spline. And also for that point, you should go and somehow replace it. Now I find the final spline, and I need to go back to the first point and select the spline and choose the tangent direction from the drop-down box and just select 1 point upstream from the first point and do the same thing for the end point. According to Wisconsin DOT recommendation, this will force the spline to be tangent to the splitter island offset. And after that, after finding the final spline, I need to create the arcs to find the best fit arcs for entry, circulatory, and exit. Then I just change my layer and try to define an arc. Just pay attention about defining the arc for entry and exit. You should go and define this arc between 50-meter arcs and entrance line. So I try to find the best fit arc, again by choosing the near option of snap. And after that, I need to just become sure about the length arc. And if the length arc is between 20 and 25 meters, it is acceptable. If not, I need to go back and recreate the arc again. As you can see here, the length of arc is 24 meters, about 24 meters, so it's acceptable for us. And I'm going to do the same thing for the central island too. And check the length of the arc. So it is small, not long enough. So I need to go and edit. And now I think it's fine. Yeah, it's 20 meters. And then for the exit, I need to go and define the arc again. And check the length of the arc to become sure it's acceptable or not. So after finding the arc, we should go and measure the radii. So I just create a dimension. And here you can have all the radii values. And after that, you need to go and calculate the speed for entry, circulatory, and exit manually. And then you need to go and see if the speed consistency condition is matched with our design or not. If not, we should come back and again recreate the arcs and measure the radius again to become sure the final value is okay and we can use it in a real design. So as you observed, the traditional method is a iterative base which is time consuming and it is totally depends on human decision. In other words, each person can achieve different values for radius and speed for the same roundabout based on different geometry of base speed, spline, and arcs. At this moment, I would like to ask my colleague to continue to show you the way that TORUS creates the fastest path, estimates speed, and check the speed consistency in comparison with the traditional method.
Thank you, Anna. Thank you, Anna. So what we'll do here is just kind of set up a little bit here. Now, part of the reason why we wanted to show the methodology manually is just to give you sort of a way to be able to compare what I'll end up doing ultimately when you see on screen. Right now, I'm just setting things up, and if you'll bear with me. Okay. Hopefully you guys can see my screen now. Okay, perfect. So what I'll do is let's take you into AutoCAD. In so much as I'm working in AutoCAD with this product, this works the same way in MicroStation as well for any of you folks that might be working with alongside the DOTs. Now, I'm not going to go too far into this software. It takes an hour and a half to actually demonstrate this. So let's focus solely on sort of what we've been talking about so far, that being able to approximate what your fastest through path might be for your specific design, as well as going through the motions of actually calculating your fastest path. So you can see on screen here, just a generic design, single lane. You can also see along the top the ribbon for the TORUS software. Now, the reason why we sort of have this method in the software is that at the time, the vast majority of people were manually designing the roundabout. So they were using their own geometry. They weren't necessarily using any software in particular besides the CAD platform that they might be using. So we needed some sort of facility for users to be able to quickly, after they've done whatever generation or editing, just to be able to go in there with the software to be able to check fastest path. Could also be in sort of the seat of the peer reviewer. Maybe they'd want to be able to just offhand check the speeds of your design. So to be able to do that, we can go ahead and just drill down here to the Evaluate Fastest Path tool. I'll go ahead and click this. And it'll walk you through a number of steps, clicking on key points of geometry on the design. So at the command line here, it's asking me to pick a TORUS roundabout, or, which case if it's manual, just click on a circle element to use as a central element. So let's do that. So we've got two circles here, this being our CI, and then the inner circle would represent the truck apron edge. So let's click on the outside here. Now it's asking me to pick a line or arc element for the entry median. Let's take a look at the through path moving eastbound. So I'll click on westbound. So I'll click on the east median here. Now it's asking me for the exit median. Let's do that over here in the west. And then it's asking to pick an entry edge, which would be on this side here. Last but not least, it's asking for the exit edge. So I'll click here. And what it does then is it goes and approximates your fastest path, as well as goes ahead and calculates the speeds based off of the approximated radii. So you can see everything sort of up here. You can see that the key offsets have been taken directly from NCHRP Report 672. You saw that earlier in the slides. With those key offsets, the software's gone ahead and approximated this path, and it's calculated then for V1, V2, V3. But also, let's take a look at, more importantly, the speed consistency here. For V1 and V2, V1 is less than V2, plus 50 miles an hour. And V3 is greater than V1, as it is greater than V2. And if you're curious in regards to what TORUS had come up with for the R1, R2, R3, you can see them noted here. And if everything's sort of fine here, you can go ahead and insert this as a report in your drawing, having all that key information. Right? Now, obviously, this one seems to be a good design, or at the very least, it produced good results. A user in this case, if they had values that are above acceptable ranges, you'd go through the motions using either AutoCAD or MicroStation to manually edit the edges, maybe change some of the entry angles potentially. But then he'd walk through, after everything's said and done, he can go back and use this tool to quickly recalculate for what the change in the fastest path would be. So this is how it's done manually. Again, it's for anybody that might have started out without the TORUS software in the beginning, or for those plan checkers that might be just checking for the safety performance of what they might be peer reviewing at the time. Let's take a look at what the case would be then if a user had used the TORUS Roundabout software to generate their design and would be going through the motions of evaluating the fastest path. Now, for this case, maybe I'm the peer reviewer, the plan checker, and I've gotten this from one of my junior engineers, and I'd want to go about checking the fastest path for this particular design. What I can do, once again, is just simply click on Evaluate Fastest Path, and then click on the TORUS design itself. And then you can quickly see that it approximates the fastest path then for the design for all approaches, and then goes ahead and calculates the different velocities as well as checks for the speed consistency. Okay. So it's using these keys offsets once again. I know as time's gone by, we're starting to hear that different locales now are coming up with supplements to NCHRP Report 672. They're starting to make design guidelines sort of their own for their particular state or jurisdiction. So if there were any need maybe to make any of those changes to these offsets, then there is an opportunity for a user to do that here. Besides the V1, V2, V3, we do also calculate for alternate speeds for the entry as well as the exit. These take into account the actual values for acceleration, deceleration as well. So it's another sort of check against what you would customarily sort of have calculated out for the fastest path. Now, I'm sure there's going to be some people that ask about this. It's a little, I'll keep it sort of high level. They're going to ask, how exactly is this software approximating this path? How different would this be from what's prescribed by WISDOT's method? I'm not going to go into too much detail, but sort of give you a high level of what it's actually doing. So let me just close this for now. And let's take a look at what's produced here. And let's maybe concentrate on this fastest path that's moving west to east. So what the software does first off is it just like what Hannah demonstrated, it offsets geometry based off of the offsets in the that you have set for the software. In this case, we're just taking the default software that's, or the default offsets from Report 672. And then what it does as a first pass is that it creates tangential arcs in the three sort of regions, at entry, through the circulatory lane, and then at the exit. Now these are sort of butted up one next to the other. It produces kinking at the very sort of at the intersections of these radii. What's done then is there's a minor reduction in the size of those radii, and the reason why is that it needs to put in for a transition between those two arcs. And then what's used to join, the geometry that's used to join those transitions then are splines. So we had originally done this as a model during the initial testing of the software with some of the engineers that were working with us. And we were finding that at least as we refined the process, we were starting to come to something that was being output that was fairly close to what these experts were coming up with manually. So with that said, it's not, given the language that Report 672 writes it in, the methodology itself is somewhat vague in that, if you have one engineer do this, his results may actually differ from another engineer working on the same job doing the same exact thing. So this in itself provides at least a little bit of consistency from one to the next, if it were on the same job. But the other thing being is that it's that sort of consistency in method from one job to the next. Now, some of the other creature comforts are sort of built in here. Again, coming from what you designers were asking for in the first place is, say I do the fastest path calculations, and say these speeds, it's yielding speeds that are above the acceptable range, maybe even along the lines of being unsafe. What do I do? How hard is it going to be for me to recalculate these speeds? So one thing that we did was we made the analysis dynamic for the TORUS generated roundabout designs. And I'll show you what I mean here. What I'm going to do is maybe we want to reduce some of these speeds here, which would necessitate me to edit the geometry that you see in front of you right now. And then maybe I might want to go into one of these legs. And the controls themselves are fairly parametric. I can go in there and maybe change some of these radii. But what I'd want to do maybe is do a heads-up design. And so much as I've got the fastest paths already being displayed, I'll go ahead and also bring up my calculations here. And just to show things off, maybe you may not do this. Well, actually, maybe at the very beginning, you may be still sort of up in the air in regards to where the center of your design might be, given the proximity to the edges maybe to your right-of-way, potentially. So what a user can potentially do here is maybe move the central island wholesale at this point. And what I'm doing at this point is just sort of moving it around. You probably go through these steps still trying to figure out exactly where the center of this design would be. But you can see that as I'm doing this, my fastest path is being recalculated on the fly, or regenerated on the fly, as well as the calculations themselves are also being calculated in real time. So being dynamic, you have less of that iterative grind that I'm sure any of the veteran designers have gone through, where you're calculating things, finding out speeds aren't where they should be, erasing everything, or maybe just editing some things, and then doing the calculation once again, and then finding out it might not be might not be there yet. Sort of those 2 step forwards, 1 step back. We go a long way towards at least eliminating that grind from the workflow. After everything's said and done, again, I could go in here and make changes potentially to the angles of these legs. Again, you'll have the values recalculated, as well as my speed consistency being rechecked. I go in there potentially putting in for greater radii, changing the value for my ICD, making it bigger, potentially reducing it depending on what my my speeds are telling me. After everything's said and done, though, we can go ahead and insert this speed report into the drawing, which has all the all the things that we need for our design report. We can also export this as a CSV file if you wanted to take into an Excel environment to potentially do further work in. But hopefully that gives you sort of a gist of how fastest path is handled through the software, as well as some of the efficiency boosts that you can get from using the software. Again, this is not everything to say about this software, let alone for this functionality. If you guys have any sort of specific questions, I believe our contact information is there on screen. We invite you to send any of those questions, whether it be on this subject or on the software in itself. Please feel free to send that to myself or to Hannah. We'll do our best to answer those questions for you. Bear with me here. Okay, Bob, I guess you can sort of take us out.
All right. Well, thanks, Johan. So for the next few minutes, Johan and Hannah, we will respond to some of the questions that were submitted during the presentation. As we start this, please continue to submit questions using the Ask a Question box on the left side of the webcast dashboard. So let's look at our first question. What is the largest vehicles per hour for this design?
Okay, I'll go ahead and field that one. So this question was coming in from Robert Hinton. Thank you very much for stopping by, and it's a good question. I think looking back at when this question popped up during the presentation, this was in and around the time that they were showing, Hannah was talking through, I think, the key offsets for both single and multi-lane roundabout. Now, this question here, what's the largest vehicles per hour for this design? That example was coming from a report 672 as a generic example for just in focus of the performance checking aspect. So in which case it was going to walk us through, it comes at the time where it's talking about the methodology for approximation of these check geometries. So it was sort of disconnected from any sort of traffic study as to what the capacity would be for that particular design. What I can suggest then is just maybe I'll refer you back to NCHRP report 672. There is a section there that talks about capacity. So it does talk through, the kind of numbers would necessitate you going from a single to a double lane roundabout or potentially more. That would be the best place to sort of search for those answers. But getting back to sort of answering your question in regards to that, what you saw on screen, that was really a generic example again, so it didn't have any numbers sort of behind it for traffic calmings. One other thing, though, I know this comes up too. Sometimes people ask what type of vehicle, what type of design vehicle is this Centerline Path 4? It approximates it for a passenger car. And some of the reasoning behind it is in terms of the vehicle that's capable of traversing the design in sort of the classic manner, it would be a car, in which case, if you guys, the bulk of us here in the United States, we're using the AASHTO P, large car. That's what it would be for. Okay, so that's that question. I can see, okay. Actually, Bob?
Yeah, let's go to the next question here. When would you make an elliptical roundabout?
Okay. I think that question came in also from, okay, so elliptical roundabouts, that's a good question, actually. Now, elliptical roundabouts, I'm not going to say I'm an expert in. I'm just trying to, it's hard to answer these things on the fly when you're trying to think of things.
Well, we'll have the questions also posted online in a couple of days, so
now,
you may want to.
With those questions that I'm unable to answer, I'm sure we're going to run out of time too. But again, we want to be able to answer all your questions. So we'll do our best here, but please take down our emails and please email us directly as well with these questions. On our side, we'll have a collection of these, and we'll be corresponding with you directly to be able to give you the answers to these questions as well. But that question in regards to elliptical roundabouts, I believe there was a little bit of guidance written in NCHRP Report 672. I'd refer back to that. Just the offhand remarks as to why you'd be using that potentially is some of them tend to be architectural features, potentially. Other reasoning behind it, they can have some speed aspect to it. Another thing being, space in the right-of-way, or maybe right-of-way constraints. But Report 672, I would look there first for that sort of guidance, and I think that's the best I can do. But okay. Thank you for asking the question.
Here's a couple, just talking about the approaches. Will this analyze a 5-leg roundabout? And also, will the software work for a 4-lane approach and exit?
4-lane approach and exit? You would be able to... Actually, that's a really good question. We can do 3 for sure. What I'm doing right now is just going to quickly test this so that I can provide an answer up front. I'm just going into that example that we looked at on screen, that very last example of a single lane. And what I'm doing right now is I'm actually increasing the number of lanes to this. So I've got 3 right now, and go to 4. No, actually the limitations of this software, currently they end at 3 lanes per leg. Can this analyze 5-legged roundabouts? Yes, it can. Now, with that said, though, fastest path is sometimes tricky with this type of designs. So it just all depends on how straight the alignment is to the opposite alignment. That would sort of govern whether there's a valid fastest through path or not. So hopefully I think that goes to answer those 2 questions.
Yes. Let's go with one more question. Did I see slowing down from 44.9 miles per hour to 15 miles per hour? And I'm not sure what example that was.
Was that talking about what we'd seen on screen early on, I guess? I'm assuming that it might be one. What I'm doing right now is just going back to the example here. 44. Okay. So based off of...
I believe it was during Hannah's example.
Yeah. I'm just wondering if that's... Because I know the torus generated roundabout had speeds in and around about 20, just under 25 miles an hour for V1, V2, and V3. So I'd assume then it would have been what we had calculated for that manual version. So I'm just running this real quick here, and I'll have an answer in just a few moments here. There we go. 44. Now, yeah, so what it was saying then is that we had a V1 of 22, about 22.28, V2 of 16, and then it was kicking right back up to 44. So in terms of the calculations for that through path, the V3 was up in the 44 region. So with that said, I mean, obviously, the designer would have to go back to this design, find a way to increase, at least introduce some sort of deflection that would decrease the speeds coming out of this quite high. Be actually quite dangerous for a person at the crosswalks in particular. Hopefully that goes to address that one particular question.
Okay. Well, as we finish up, you'll be able to download your certificate of completion from the Event Resources section on the left side of the screen. And after downloading the certificate, you can enter your name in it and print and save a copy of the PDF. The certificate will be available through the end of today only. A hard copy will not be mailed or emailed to you. If you missed our note at the beginning and you were watching the live webcast with a group on one person's computer, please download the multiple viewer registration form and complete and submit the form to receive your credit. We need this information in case you are audited and we are contacted to verify this continuing education activity. Additionally, this webcast has been recorded and will be archived on csengineermag.com/continuingeducation. For viewers of archived webcasts, click on the quiz button at the bottom of your screen to take a quiz on the presentation. Archive viewers must pass a quiz in order to download a certificate of completion. All of the answers to the questions submitted today will be available online within a few days at csengineermag.com/continuingeducation. So please check there for further discussion about today's topic. As we conclude, you should see a webcast evaluation survey. We appreciate your feedback, which helps WAG Group and sponsors such as Transsoft Solutions plan future webcasts. So thank you to Johan and Hannah and to everyone who joined us. This ends today's webcast.